Welcome to Red Dragon Mission Training. Training number 6, Circular Motion. This video tutorial will cover the following learning targets. Circular motion uses some very specific vocabulary. Centripetal force is the force exerted towards the center of a circular path. This is what allows objects to move in circular paths. We use the variable F sub c. It's a unit of newtons. The radius is the distance from the center of a circular path to the edge of the circular path. The variable is r, and the unit is in meters since it's a measure of distance. Visually, this is what the radius looks like. We have a circular path. The radius is line segment QR. When we refer to the mass, we're talking about the mass of the object that's moving in a circular path. The variable is m for mass, and its unit is kilograms. When an object moves in a circular path, it makes revolutions or laps around the circular path. The frequency is the number of revolutions made in 1 second. So it's how many revolutions or laps around the circle the object can make in 1 second. The variable for frequency is a lowercase f. The unit is revolutions per second, or hertz, represented by capital H, lowercase z. The reciprocal or inverse of frequency is the period. Period is the time it takes the object to make 1 full revolution. The variable for period is represented by capital T. It's a very specific time, so it's t, which means its unit is seconds. Frequency and period are easily confused. Frequency is how frequently it makes it around in 1 second. The period is the time period. It's how much time it takes to make 1 full revolution or lap around the circular path. In centripetal motion, when we refer to velocity, we're talking about the straight line speed that the object would move if there was not enough force to stay in the circular path. If an object moving in a circle leaves the path, this is how fast it's moving. Centripetal force is a new category of forces. It's not a new force like gravitational or normal force, for example. Anything that can exert a force can exert a centripetal force. For example, a rope or a string can cause a tension force, F sub t. In this case, the space shuttle is trying to use a probe on a tether to create artificial gravity by spinning the tethered probe around while the shuttle remains in the center. Gravity commonly can cause centripetal force. This is how satellites stay in orbit. This is how the International Space Station stays in orbit. In space especially, if we look at the wall and friction combination, now these are sci-fi examples, but they present real centripetal forces. A wall, or normal force, can create friction. For example, if your car goes around a curve or up a circular on-ramp, you may feel that you're pressed against the wall or the side of your car. Friction is what's keeping your car on the road as you drive in a circle. Let's look at an overhead picture of centripetal motion. Imagine you have an object attached to a string and you're spinning it over your head in a circle. Which direction is the force acting on the object? What is keeping that object spinning in a circle? It's attached to a string, so it's being caused by a tension force, but that force is moving towards the center. As you spin the rope and object around in a circle over your head, your hand is pulling the rope inward towards your hand. Centripetal forces are center-seeking forces. So as this object spins around, the force that's keeping it in is caused by the string or rope pulling it inward. towards the center of the circular motion. Other forces work the same way when creating centripetal force. A satellite orbiting the Earth is constantly falling towards the center of the Earth due to gravity. Gravity is causing its centripetal force. When a car turns around or does a donut in a parking lot, friction is pushing against the tires, pushing it inward towards the center of the circular path. If the string broke in this case, in which direction would the object continue to move? If the string were to break, there would not be enough centripetal force pulling the object inward, which means there wouldn't be enough force to keep the object moving in a circle. If the string snapped, there wouldn't be enough force, and the object would move straight. Newton's first law describes inertia and momentum. An object in motion tends to stay in motion. So because of momentum, that object's going to move straight off. Specifically, it's going to move tangent to the curve. A tangent line is a line that crosses or intersects with a circle at only one singular point. It also creates a 90-degree angle with the radius, or in this case, the string. Other forces act the same way when creating centripetal forces. A car driving in a circle is kept in that circle due to friction. That car drives on ice, there might not be enough friction. Just like the string didn't create enough force, friction won't create enough force, and the car will spin out and slide straight off on the ice. We can calculate the amount of centripetal force using these three formulas. Each formula includes the mass and the radius of the object, or the radius of the object's path in a circular motion. The first formula you use when velocity is involved with the problem or scenario. The second equation you'll use if the period is involved. Capital T is period. Period is the amount of time it takes to make one revolution. If the frequency is involved, you'll use the last formula. Frequency is how many revolutions the object makes in 1 second. Newton's first law helps to explain how an object moves when it leaves a path. Newton's second law, force equals mass times acceleration, helps us find what's called centripetal acceleration. On all three of these equations, the left side of the equation is force. The first variable in all three is mass. If I get rid of the mass and just look at what's left, I have an acceleration formula. So if I take out mass for all three of my equations, I'm left with just acceleration. These three formulas can act like 6 different formulas. If you calculate the acceleration using any of those three formulas, all you have to do is multiply by the mass of the object in order to find the amount of force required to keep it in a centripetal orbit or centripetal motion. If we take advantage of the curvature of the Earth and the Earth's gravitational force, we see that an object that is projected at that velocity will eventually fall due to gravitational forces. If we keep that object moving at that velocity and we assume that it'll keep falling, we can keep an object in orbit. Things like satellites, space shuttles, and space stations are in orbit because they are in constant free fall. They move just fast enough that as they fall, they keep missing the Earth. They're in a centripetal motion around the Earth. This force is caused by gravity. A 910 kilogram satellite is moving at 8,000 meters per second at an altitude or height of 225,308 meters. What's causing the centripetal force? On your own, answer the question and come back when you're ready. Gravity is causing the centripetal force. As that satellite orbits around the Earth, it's constantly falling towards the Earth. What is the radius of this satellite? In this case, we know that the satellite is 225,308 meters off of the Earth's surface. The Earth itself has an extra radius of 6,371,393 meters. So the full circular path has to be the altitude or height of the satellite off the Earth and the radius of the Earth itself. So we add those together, we get a nice big radius to work with. What is the satellite's centripetal acceleration? Use the equations in the bottom right-hand corner. Remember, these formulas represent centripetal force. Centripetal force equations are just acceleration equations with mass. To begin this problem, I would select the proper formula. Since I have been given the satellite's velocity, I'm going to use the formula that involves velocity. I look at my formulas, I see m times v squared divided by r. I'm not going to include mass if I'm finding acceleration. Now I just plug and chug. The velocity is 8,000 meters per second. I know the radius. I calculated that by adding the satellite's altitude to the Earth's radius. I'm going to take care of my exponents first, then take care of division. Leaves me with an acceleration of 9.7 meters per second squared, which, considering this object is kept in a circular path or orbit around the Earth by gravity, it's interesting that it comes out to be very close to gravity's acceleration. What is the satellite's centripetal force? On your own, find the satellite's centripetal force. Your formulas are in the bottom right-hand corner. There are two methods for finding the centripetal force now that we know the acceleration. Since I was given the satellite's velocity, I'm going to use the formula that includes velocity. Plug everything in. Mass is 910 kilograms. Velocity is 8,000 meters. And I have the radius of the circular path that the satellite's following. Take care of my exponents first. Multiply. Divide. And I should be left with 8,828 and change newtons. That's a lot of force because this is an object that's very far off the Earth's surface. We can also find the centripetal force by multiplying the mass of the satellite times the centripetal acceleration. Since the centripetal force formulas include mass times acceleration, similar to Newton's second law, F equals m times a, I can take the acceleration I found in the last problem, 9.7, and multiply by the mass of the satellite. Should get the same answer. Now, in this case, they come off a little different due to rounding. Both of these answers would be acceptable. We can also find how long it takes for the satellite to make one trip around the Earth. This is called its period. The amount of time it takes to make one revolution is the period. On your own, select the proper formula to solve. You can also use an equation derivation chart if you want to find t by itself. Because we're looking for the period, I'm going to use the formula that has the capital T. I'm going to take the derivation of it to make calculation a little more approachable. Simply substitute all the values in for the variables. Whenever you have a formula that is a rational expression or a big scary fraction, simplify the numerator, then simplify the denominator before turning it into a decimal. So I'm going to multiply and take my exponents up top. Now I'm left with one value in my numerator, one value in my denominator. It's a lot easier to divide those when they're each simplified. Divide top by bottom to get a final answer there. Remember to take the square root. That's my last step in using this formula. It takes about 5,396.76 seconds.